there are many design properties to a piece of wood in general, or a piece of steel, or concrete, or what have you. One of the most notable ones is what we call E-value, or modulus of elasticity is what it stands for. Basically, it's how much does it bend, or what's its resistance or strength in bending. Okay, so the higher the E-value, the stiffer that piece of wood will be. Okay. Typical trees that we would use to manufacture LSL, timber strand LSL, would be aspen, poplar, trees that are very, very weak. Have a very low E-value, 0.8 E. And the average kind of spruce, pine, fir mix is normally be around 1.3 E. So aspen and poplar are very weak wood species, and they never grow to be very big. They kind of grow sporadically, and after about 10-15 years, they end up falling over and dying before they actually get any bigger. It's almost like a weeded forest. So it's not really used, those wood species aren't really used for much, at least not in the construction industry. So what we've done as an innovation, as a product, is we've taken those kind of underutilized wood species that grow fast, they're in abundance, but they're not used for anything. So we take that weak material and we chop it all up into long strands, because it doesn't matter if we have a nice big billet, it doesn't matter, we're chopping it all up in this. And then we orient it all in the same direction. So I have a really small piece here, but if you look, it looks a little bit like OSB if you really looked at that, but it's much larger flakes, much longer in size, and we orient them all in the same direction. And then we press it, it's a microwave technology, we have some secret herbs and spices, if you will, out comes LSL, okay? And that's what timber strand is. We can make it in a variety of strengths. Our rim board is typically 1.3 E. We make studs with 1.5 E, and our beam part is 1.55. We actually made a 1.7 for a while. That's just a question of what wood basket we're pulling from, how we want to build what grade of wood fiber we're pulling from the forest, and how we orientate it and all that kind of stuff. Okay. So timber strand has a lower, you'll see later with the next beams, if you just speak of beams, 1.55 is the timber strand, okay? The microline, we'll see the next slide, is 1.9, and the parallel is 2.0, okay? So the E value is lower in timber strand, but we use significantly more of the tree. Remember a while ago it was 40% roughly for solid sawn lumber. Timber strand we would yield about 76% of the raw material goes straight into the product. And what doesn't go straight into the product, like the bark, the branches, the leaves, and all that, we actually burn to fuel the plants. So we're virtually using 100% of the tree. So we're not having to send it off site to be mulched up or paper or something else. So it's really, if we want to speak of environmentally friendly wood products, you don't get much better than this. Okay. As with all products that we make here, the glues that go in there into the product are essentially inert once they're cured. Once they come out of the, they're cured, so they don't smell. The only smell that you smell is wood. So there's no off-gassing or health hazards or something like that. Kind of resins that we use. Okay. So that's timber strand. You'll see here what's special about timber strand. It's the only beam on the market that you can cut large holes in it. And that's because of the design properties. It has a lower E value, but it has a much higher strength in other design properties, such as shear. Okay, the effect of wanting to slice off at the support. So if I have two walls here and I have a beam from point A to point B, and there's a lot of load here, while the stress here at the support point I'm wanting to shear off, timber strand performs very, very well. It has a lot of shear strength, more than other beams on the market. And also, because of its composition, it's very, very dense, still workable. You can cut it with a saw, you can nail into it and all that stuff. But it's a lot denser than a piece of SDF would be, a piece of regular 2x4, which makes it very strong in crushing. Okay? So the role that timber strand has to play would be more for really shorter spans where bending isn't governing. Okay, the longer the span, typically the bending becomes more critical. But if you have a shorter span, but really heavily loaded, then shear or crushing becomes more becomes critical, becomes the real governing factor. But if you had a 6-foot patio door that had a big point roof from a girder truss up above, it's not how much it's going to bend that's going to be really governing, it's how much it's going to want to slice off out of there. Okay? Or how much bearing length you need, because there's so much load there. So that's where timber strand really shines. Okay? So lower E value, but higher in other respects. Micro-lam, the way LVL is made, is basically we take a billet, you peel it, like a roll of toilet paper, you peel the log into veneers. It's a real thin veneers, kind of like just like plywood. And then each of those veneers is graded, electronically graded. It's a real scientific process. And then we can basically overlap those veneers in whatever strategic way, putting different grades in different places in the billet, and it's pressed together with hot plates, top and bottom. And out comes LVL. Okay. Now, what was innovative at the time when this was invented, back in the early 70s, I think it was, plywood existed back then, but the manufacturing process is such that there was a limit to how thick you can make this before the hot plates coming on the top and bottom would burn the veneers before you can cure the inside grooves. So the manufacturing process, what we know today is LVL, was the innovation at the time. And now many other manufacturers make it as well. Okay, so we make LVL in 1 3/4 thick. There is actually one manufacturer I know that makes it 3.5 inch thick. It's very rare. We don't really see it much in this market, but it can be done. Timber strand, to rewind here, all of the beams are all made in multiples of 1 3/4. That's kind of the standard in the industry. So timber strand made 1 3/4 and the solid billet of 3.5. So 2 times 1 3/4. Here we go into 2 ply. So that can be made in 3.5. We only make 1 3/4 of this, but see the parallel can be made thicker. So we take trees to make micro-lam or LVL. We take trees, kind of like fir and grades or species of trees like that are generally 1.3 E in that range, and we make a 1.9 E product. Okay. The yield is a little bit less. We saw 76% of all of it with timber strand, and this is 52. It's lower because when we start peeling a log, the first few laps around the billet never come out as perfect, nice sheets of wood because there's branches, there's bark, there's trees a little crooked. So it's never perfect veneer. So those veneers were traditionally discarded, or remanded to something else. And then you can only peel or unravel the log so far. You're left with typically a core that's about 3 inches in diameter, and that as well doesn't go into the product because we can't unwind it that small. So we usually would sell that back to lumber treaters, and they make landscape products with those. Kind of, you see those 3x3 mini ties sometimes at your local hardware store. So that's kind of where that stuff comes from. Okay. So there's less of the product that goes right back in there, less of the tree that goes right back into the product. Okay. But still, using far more of the build than you would with solid solid. Paralam, remember we said that the outside of the billet is the strongest wood fiber? Well, what we do with Paralam is we take all those imperfect veneers that we can't make LVL with, and we cut them into longer strands, and we work them all in the same direction. And Paralam is done with a steam injection process, and that allows us to get the same type of trees into a higher E value, to 2.0 E as opposed to 1.9. And we'd be able to even higher if we wanted to be real selective in the species of trees we use, but as an average, we manufacture a product of 2.0. Okay, and what's unique about Paralam is that we can make it in very large, we can press it into very large billets. So we commonly see beams up to 7 inches wide by 18 3/4 inches deep. So real big, heavy, solid pieces of lumber. And we run into that a lot into kind of post and beam or real architectural type stuff. A lot of architects and engineers like that. It's very similar in terms of strength and fire performance and all of that to heavy timber, to old growth heavy timber, but it's obviously much more readily available.